Okay, so welcome back everyone, and this is the fourth talk in the series of the scalar curvature rigidity for manifolds with cone singularity will be the today's topic in the spin geometry and scalar curvature rigidity series. So Lucas will going to continue his talk. So Lucas, it's over to you.
Yes, thanks for the introduction. Okay, I will recap from last time, Llarull's theorem. So it was kind of the original scalar curvature rigidity theorem. And what we have a closed connected spin manifold, dimension at least 2. Then we have scalar curvature that is bounded below by the scalar curvature of the n-sphere with respect to the round metric. And we also have this comparison map F, which is supposed to be smooth and has to be a non-trivial in some sense. So this is this degree condition on F. And then in dimension 2, we need that it's one Lipschitz, which means that the length does not increase. So yeah, if you look at distances between 2 points, then in the image the distance has to get smaller, not bigger. And in dimension at least 3, we can relax this a bit and assume that F is area non-increasing, which is the area analog to length non-increasing. And I would say these are quite mild assumptions, and we get a very strong conclusion, namely that F is a Riemannian isometry. So basically M is already a round sphere. And I wanted to give you a small overview of works that follow this, or directions that people generalized this theorem. Probably the first were Goethe and Sammelmann in 2002. And basically, they replaced the n-sphere by some manifold which has or with Riemannian manifold where the metric has positive Riemann curvature operator and also a topological assumption, namely the Euler characteristic is supposed to not vanishing. That's important for the index computation, the Euler characteristic. So yeah, actually this theorem is a bit more general because it allows the domain and the image of F to have different dimensions, and the conclusion is then that it's a Riemannian submersion. Yeah, and then some years later, in 2021, Lott generalized the Goethe-Sammelmann result to compact manifolds with boundary. In this case, we also need some assumptions on the curvature on the boundary, namely we have assumptions on the second fundamental form there. And then a result from a kind of different perspective is the one from Brendle. Namely, he showed a rigidity theorem for convex polytopes. And then also in 24, the Brendle, Hanke, and Wang showed that Llarull is also true in the case where we remove 2 antipodal points of the sphere. So they used on the manifold Sn with antibodal points removed, we can write this as a Rob product metric. And they use this structure to actually get this result. So there's a more general conjecture of Gromov, which says that we can remove so finitely many points from the sphere, and Llarull will still be true. And kind of all these results are driven by conjectures of Gromov. And so the other generalization that I showed you last time is also of this kind, namely, so the even dimensional case is due to Cecchini, Hanke, and Schick. And so the odd dimensional case, we uploaded a paper earlier this year where the same authors and myself worked on. And namely, what we do is we can relax the assumption on the metric to allow metrics that are not smooth anymore, rather than have some Sobolev regularity. And here this P bigger N kind of relates to the Sobolev embedding theorem. So that's the boundary case of Sobolev embedding. And this is also needed to define this scalar curvature of G in this distributional sense here. And we also relax the condition on F, namely we don't assume anymore that F is smooth. It can be Lipschitz. But we still keep assumptions that F is 1 Lipschitz and for n equal 2 and area non-increasing for dimensions at least 3. And then the conclusion is that then F is a metric isometry. It's so we cannot conclude it's a Riemannian isometry. That's would be too strong. But as map were considered with the Riemannian distance functions that are induced from the metrics, with respect to these, this map will be an isometry. And so last time I sketched the proof for the even dimensional case. So today I want to say something about the odd dimensional case of it. And one remark I wanted to make is that actually Lee and Tam, also in the year 2022, showed the theorem for all dimensions, but in the case where F is 1 Lipschitz for n is 2. So they used Ritchie flow methods, but they couldn't get a handle on the area non-increasing part. So this was still open. And before I come to the proof, I want to show you another result that is also in this paper from 25. You know, it's also in the topic of this talk, namely manifolds with singularities. And for this, I first have to make some definitions. So assume that M is a closed manifold, and then assume that we have some number theta between 0 and 1 and a family, a smooth family of metrics. So on this interval from 0 to theta with elements in the smooth Riemannian manifolds, smooth Riemannian metrics on M. So this is a smooth family of Riemannian metrics. And also assume that we have a C2 metric on M such that GR converges in the limit R to 0 to G0 in C2. And we also need some assumptions on the derivatives, namely the derivative of R, and we can allow some that it converges in some sense. We don't need that it's actually converging. And for the second derivative, it can even more diverge. Then, so the metric CGR, which is defined as the work product metric, or let's say generalized cylinder metric on 0 beta times M, is called a generalized cone metric. And these assumptions on the derivatives are made so that we have some handle on the scalar curvature, because for scalar curvature you need to differentiate twice. So we also need some conditions on the first and second derivatives to kind of handle the scalar curvature. And then we can define manifolds with singularities, namely a Riemannian manifold is a smooth Riemannian manifold with cone-like singularities. If so, there exists some compact subset, and is also such a number theta between 0 and 1, and a Riemannian isometry nu going from W without K, with the metric restricted to this part, to a generalized cylinder metric. So with the boundary of K and that is a generalized cone metric. And the picture that you should have here in mind is, so we have some manifold W, which has a boundary. This is this K here. So this inner part would be K, and there's some cone attached to it. So this would be a kind of the straight cone. I should say, so straight cone would be something where this GR here is constant. And okay, so this would be del K. And yeah, we have the cylinder. And for these kind of manifolds, we also have a rigidity theorem. We call it theorem 3. It's in the same paper that I mentioned above. And we assume that we have a manifold with convex singularities in dimension n+1. So Riemannian spin manifold on like singularities, and n should be at least 3 odd. So it starts from dimension 4. And again, we assume that the scalar curvature with respect to this metric should be bigger or equal than the scalar curvature of the metric in dimension n+1. And we also have a comparison map going from W to Sn+1. Should be Lipschitz. And area non-increasing. Almost everywhere. And also, we assume that the degree is non-trivial. And then as a conclusion, we get that F is a Riemannian isometry onto a punctured sphere. So these cone points, you can actually add these cone points to the manifold. You get a kind of a compact set, which is no longer, or in most of the cases, no longer a manifold anymore, but you can take the metric completion of this manifold, and these cone points will map to points in the sphere, and if you take them out, you get this Riemannian isometry. So yeah, that's the second rigidity theorem that I wanted to talk about. And now let me first come back to the proof of theorem 2, because here the odd dimensional part is still open. So let's say part 2. And actually, I first want to talk about the even dimensional case, because last week I just said this as a black box, but it's convenient now to talk about this, so that's then easier to explain why we do in odd dimensions what we do. And that's the step from local isometry to metric isometry for an even. There are said that so at the point where we had that it's a local isometry almost everywhere, I said that we have to show that F is either orientation preserving or orientation reversing almost everywhere. And then we use a black box which goes back to Schick. But actually, one can illustrate this quite easy why this assumption here, or this makes sense why we have to show this. Namely, if we look at the absolute value map going from R to R, This is a perfectly fine Lipschitz map. It's actually a local isometry almost everywhere. But so if we look at the Euclidean distances, so the distance between -1 and 1 is of course 2, but in the image the distance is just 0, so this cannot be a metric isometry. And what we see here is that here on the right side it's orientation preserving, and on the left side it's orientation reversing. And if we show that the map is actually orientation preserving or reversing everywhere or almost everywhere, then these kind of folding points cannot happen. And this picture, you can also imagine this in higher dimensions. These folding points might not be points, but subsets. Yeah, but that's kind of the reason why this assumption here or this condition here makes perfectly sense. And the thing is that this only works quite well in even dimensions. So this is because, so let's take some harmonic spinner. As I said last time, we find this in this positive Llarull bundle. So this sigma m splits in even dimensions in these two sub-bundles. And this harmonic spinner lives here in this positive part. And from the Schrödinger-Lichnerowitz formula, we did this estimates. We get first that EI Clifford multiplication EJ, and then the second factor F star EI F star EJ. Acting on this harmonic spinner is actually the identity. So I mean, I can go back to last time. This was precisely from here to here. So we said in the end that all these inequalities have to be equalities. So in particular, also this here has to act as the identity. So that's precisely the point where we get this property of this harmonic spinners. And the second point is that also from the estimates that this is a parallel spinner almost everywhere. And this says that the absolute or the norm of U as function on M is constant almost everywhere. Let's say this is 1 and this is 2. So let's assume that we have some x such that the differential exists in this point. And we have this volume forms from last time. So we have it on M and also on the N sphere. So this is the volume forms. And these were given by I to the k E1 Clifford multiplication to En. And I said that d squared give 1, and the sigma m plus and sigma m minus are the plus and minus 1 eigenbundles of this element here, this volume forms. So since the harmonic spinner lives in the positive part, here this omega Cm tensor omega Sn applied to U will act as the identity. So this is part 3. And we already know that F is a local symmetry. So for these volume elements, we took oriented orthonormal bases. So if we, so this is also a orthonormal basis, but if F is orientation preserving, then this will be an oriented basis. But if F is orientation reversing, it will be a non-oriented orthonormal basis. So that's why here we get a plus and minus 1, and I also have this I to the k. So this is if F orientation preserving and minus orientation reversing. So from this we get that I to the 2k E1 to En tensor F star E1 up to F star En applied to U. So from part 3 we know that this is plus minus U depending on whether F is orientation preserving or reversing. And on the other side, we can apply here this first property. And now dimension is even, so we can pair all these basis elements in pairs, so E1, E2, E3, E4, and so on. And we actually get that this is minus 1 to the k U. So equation 1 applied iteratively. And so now we just compare these two sides and see that F is orientation preserving in X if K is even, and reversing if K is odd. And X was arbitrarily, and since U is constant almost everywhere, or the norm of it, it does not vanish anywhere, or at least not up to a set of measure 0. So this all holds almost everywhere. And now we use this black box of Reshetniak that F is a metric isometry. But from this, you can see that for this, we really need even dimensions, because in odd dimensions, always one pair of EI tensor F star EI would stay, and we cannot conclude here this equality. So what do we do in odd dimensions? In odd dimensions, we kind of transform this whole problem into an even dimensional problem. And to turn the n sphere and an n+1 sphere, the natural thing is to consider the spherical suspension. Namely, Sm will be m times 0 pi with the product metric given by er squared plus sine squared rg. And this construction is functorial in the sense that we also can transfer the map F into a map SF, going from the suspension of M to the suspension of Sn, which will be just the n+1 sphere with north and south pole removed, and the metric on Sn+1. So in pictures, you can think of some manifold here, which is supposed to be M, and then you consider such a suspension, so where this M gets scaled when approaching the points at the north and south pole. And in the north and south pole, this all will collapse into a point, which we remove so that it's still a non-compact manifold. And on the other side, we just get the n+1 sphere. And the nice thing is, also this is Sm, the nice thing is that the scalar curvature with respect to the suspension is then, so we started with that this is bound, the scalar curvature of G is bounded by below by n times n-1, and this now gets upgraded to the 1 dimensions higher, which is the scalar curvature of the n+1 sphere. So we again are in the Llarull setting with one downside, namely if F is area non-increasing, this does not imply that SF is area non-increasing. So this is because, I mean, area non-increasing means, or can mean that you can stretch in one direction and contract in the other direction vectors, and the area will still be smaller or equal than 1, but you have stretched one direction and contracted one. But the this R direction here of the spherical suspension kind of stays with norm 1. So if you pair or consider the area between this R direction and this extended direction in M, then the area will actually increase. So this area non-increasing property will not transfer to the spherical suspension. So the solution is that we first show that F is a one Lipschitz, because that travels over to the spherical suspension. So in fact, we actually show that F is a local isometry almost everywhere. And for this, we use spectral flow. And then we can play the whole game with the spherical suspension. but we have to do the whole proof again because we need this harmonic spinner, and we need where do I have it? We need this property here, and for this we have to do all again. It sounds a bit weird, but that's how we have to do it. And then, since we now are in even dimensions, we can use this trick again where we show that F is orientation preserving or orientation reversing almost everywhere to actually get that it's a metric isometry. But there's one caveat that I should mention. One problem is that we have the Schrödinger-Llarull formula only for p bigger n plus 1 on the on the spherical suspension, because the Schrödinger-Llarull formula holds in this Sobolev setting if p is bigger than the dimension. We now increased the dimension by 1, but we didn't increase p. So in order that this proof holds, we actually need to assume this, but it's a bit stronger than what's in the theorem. So we think that it's still can be worked out with the assumption p bigger n. One has to probably refine the analysis a bit. But we didn't go through with it because with the what I showed you before, or the small remark that, where do I have it? Lee and Tam showed the theorem in the case where F is 1 Lipschitz. And at the moment where we showed with Ritchie flow, with spectral flow, that F is 1 Lipschitz, we can just apply Lee and Tam to get the result. But we still thought that it might be interesting to have a purely spinner theoretical proof of it. And it also allowed us to do the introduce a newer setting where we can also prove this Llarull theorem for cone manifolds. So yeah, that's that. Actually, I want to leave some discussion on the spectral flow, because it's considered that as the odd-dimensional analog of the Atiyah-Singer theorem. So this might get very important in the future. And so this definition of spectral flow is in quotation marks because it's not totally rigorous. But one can make it rigorous. So let's assume that we have a continuous path. So continuous is also in quotation marks because I don't want to explain now what this actually means in this context of self or joint Fredholm operators, dt, where t ranges in some interval ab. The spectral flow is the number SF of dt. We take the number of, so since it's self-adjoint, all eigenvalues or all the spectrum will be on a real line. And the spectral flow is the number of eigenvalues that cross from minus to plus. So they cross the eigenvalue 0. And we subtract from it the number of eigenvalues that pass from positive to negative. So that's the spectral flow. And I mean, in our context, it's interesting because if the spectral flow is non-zero, this means that there's, for some t, there's a harmonic spinor of this operator. And there's a theorem of Getzler computing the spectral flow for a certain class of operators. Namely, if we have a odd-dimensional manifold, it's closed, connected, and spin, and D is supposed to be the Dirac operator on the spinor bundle, tensor a trivial bundle. So this is the trivial CN bundle where n is some natural number, so the sum natural number n. Then assume that we have a smooth map from n into the unitary matrices of n, of, let's say, yeah, unitary matrices acting on C to the n, smooth. And we consider the family of Dirac operators of the form. So it's a convex combination T U inverse BU. So one can interpret this in K-theory. So I won't go into this more deeply now, but from a theoretic viewpoint, this is actually exactly what you want to do, let's say, to get an analog of the Atiyah single index theorem. And okay, there's some prefactor involved by I. And then the rest very much looks like the Atiyah single index formula. Namely, we take a head class and wedge it with a Chern character, but it's not the Chern character of a vector bundle. It's a odd-dimensional analog of it, and it's a Chern character of this map U. Okay. As for the Atiyah single index theorem, I will not really explain what these characteristic classes are, but you can define them using John Wall theory, for example. And there's a special case where Getzler computed this expression, namely for the M sphere, the spectral flow of this family is just the degree of this map U into the unitary maps. So yeah, from a theoretic viewpoint, this might be quite satisfactory, but it seems to, or at least as far as I know, it seems to be quite difficult to find such unitary maps such that we get actually a family of operators where we can have a non-trivial spectral flow. Actually, up to now, it all comes down to one manifold where we can actually compute this, namely the sphere. And to explain this, let me first introduce a new or a modified connection, namely for a smooth spinner on some manifold M. We set nabla T xu. So nabla xu. So nabla is supposed to be the spinner connection. Maybe write it this way. And then we modify it by applying this vector, this tangent vector x, by Clifford multiplying with the spinner. And so nabla T parallel spinners, they have a special name. They are called killing spinners. And they are quite rare, and only for special manifolds we find them. And yeah, one important example is, so let's write 2k or 2k plus 1 for the dimension, depending if we are in even or odd dimensions. And for t equal plus minus 1/2, the spinner bundle of the n sphere can actually be trivialized. Can be trivialized by killing spinners, by parallel spinners. So, i.e., there exists a trivialization from sigma Sn to Sn times c to the 2k. And so we get it for plus 1/2, and we also get it for minus 1/2. So actually, on the n sphere, these killing spinners are available in abundance. But on other manifolds, it's quite rare that you find these killing spinners. And now let's consider going back to this setting where we have such a comparison map from M going to Sn, and we consider the pullback bundle E, which pulls back this trivial bundle, which again will be trivial. So we kind of pull back this, which is via this trivializations, the same thing then pulling back the spinner bundle over the n sphere. And we equip it with the trivial connection. With the trivial connection, I mean just the differential. And we consider the twisted Dirac operator of it. So these trivializations induce on the polar bundle, namely u plus minus going from e to m cross e to the 2k. And we set u as, so we, from the trivial bundle, we go back to the spinor bundle and then again to the trivialization. And this we can consider as map into the unitary matrices on C to the 2k. So that's this unitary map that's appearing here. And so this spectral flow with respect to this family, we can now compute, or was computed by Li, Su, and Wang, and says that the spectral flow is actually the degree of f, which was assumed to be non-zero. And by the definition of the spectral flow, this means that for some t in 0, 1, there exists a harmonic spinor in the kernel of et. So kind of we reach the same conclusion as using the Atiyah single index theorem in even dimensions. And now we can do the same game and insert this harmonic spinor into the Schrödinger-Lich-Llauridge formula, do the same estimates, and get that f is actually a local isometry. Good. So before I go to my last part, are there some questions? I hope that I wasn't too fast now, but I wanted to include the spectral flow here because it's kind of an important concept. So the last part is actually, now we have established this here that f is one Lipschitz or even local isometry almost everywhere. And now we go to the spherical suspension here. And this spherical suspension is, we can interpret this as a manifold with cone-like singularities, because here this north and south pole will be cone singularities as I defined here, this definition here. So this will be this a example of generalized cone metrics. Yeah, the thing is that so the spherical suspension of M, it's a non-compact manifold, and in principle for a generic non-compact manifold, index theory is usually quite hard or even impossible. So there's no, a priori, there's no reason why the operator should even be Fredholm. But in special cases like cone manifolds, you can actually show that the operators are still Fredholm, and you can also compute the index. And to do this, we introduced a abstract analytic setup, which can treat cone operators. So I will not go into the technical details here, because this is a bit, this whole setup is a bit technical and subtle. I only want to explain how this situation looks like in the spherical suspension case. But I should also say that that's not all from ourselves. So this goes back to work of Giga and also Brinning and Seeley. So let's consider the spherical suspension as above. So just as a reminder, this was this cylinder with metric r squared plus sine squared r g. So you can do the same thing with this generalized cone matrix, but for simplicity, assume that we are in this setting now. And we can also find bundle isometries going from this plus and minus eigenbundles of the volume element restricted to a some fiber over this interval. So this general fact that this is isometric to the spinor bundle of the dimension 1 less. And this is also compatible with Clifford multiplication. I would have to explain some stuff here, but let's just assume that we have this now. And I want to consider just one of the cone points, namely, let's look at the cone point. Let's say that's the North Pole. The same works for the South Pole. And now if you use parallel transport of sections in the spinor bundle of M along your basic lines 0, 1 times big 1 point in M. So kind of let's say here we have this interval 0, 1, and somehow here we have sigma M, and this is kind of extended to that need more space. This whole is sigma Sm or S sigma plus Sm. Then we kind of have some spinner here, and we extend it by parallel transport on this whole spinner bundle over Sm. And okay. So this parallel transport, from this we get isometries. From the Hilbert space of sections to sigma plus minus Sm with the volume element of Sg, say phi plus minus 2 L squared. So there are two sections from the interval 2. There are two sections of M, sigma M, with, okay, I need more space. With volume element, we have this such a, so the warping function appears here in the volume element, and we have the volume element of G here. Okay. And the Dirac operator using these isometries looks like, so you take the spinor connection and you split it into the R direction part and into the direction of the manifold M, and it splits into differentiation in R direction plus n half cotangent of R. So this is not arbitrary. This is the mean curvature of this kind of product that we take. So in general, here would be the mean curvature plus 1 over sine R dm. So the operator kind of takes a product form now, and I should say we consider here the untwisted Dirac operator. So yeah, with the twisted operator, you would get additional terms here. But for simplicity, let's stay with the untwisted one, and we can get rid of this mean curvature term here by incorporating this weight on the volume element into the sections. So namely, we compose these isometries with multiplication with sine n half R. So one part so if we have this norm here, say that's side remark, we have this L2 norm here, somehow looks okay. We integrate over the line and then over M, and this will be something like this, sine n d wall G dr. And we kind of put half of the sine to the n into V and 1/2 into the U. Okay, I should write here then sine n half. then we get isometries L2 sigma plus minus as what's G. So I will call this phi plus minus tilde. And this now lands in the L2 space, going from the interval to L2 m sigma m. But now we only have the volume element of G. So now this space here is independent of R. So this is a fixed Hilbert space. In our paper, we call it L for link. So it's the everything that happens in M is usual to call it link. And if we look now at the formula of this operator, with this modified isometries, then we actually see that this cotangent term here disappears, so it's kind of incorporated in the section in the spinors, and we are left with 1 over sine r dm. Okay, I didn't say this. dm is the Dirac operator on M. And now we want to do analysis with this. And so we can do analysis with a straight cone where sine squared of r would be replaced by r squared. So what we do is we kind of do we add here this term that we would get from a straight cone, namely 1 over r dm, and kind of regard the difference here as a perturbation term. And okay, what we want to show here is that the operator is a Fredholm operator, and this is now let's say standard theory when you do PD theory for elliptic equations, for example. And what we do is we construct explicitly a parametrics for V plus. And parametrics means this is an operator, a bounded operator from L2 sigma plus Sm going into the domain of the operator. Let's say, so we want closed Hilbert spaces, so let's say we consider here the minimal closed extension of T. So this should be a bounded operator, such that it's kind of a inverse operator up to compact operators, meaning that P applied from the left is identity plus some additional term, and P applied from the right is also identity plus some additional term, and these additional terms here are compact operators. And the existence of a parametrics for an operator, this is equivalent to the operator being Fredholm. So existence of a parametrics for t plus bar, this is equivalent to t plus bar being Fredholm. Okay, so how do we construct this? So so ignoring the perturbation for now, for this part in front, we can actually construct a honest inverse operator and then modify it so that it gets at least over this 0, 1 part here, gets a parametrics there. And then we still have the parametrics part of the inner part. So maybe let's go to this picture for cone manifolds. So we construct the parametrics first on the cone part. We can do this quite explicitly. And on the inner part here, we can use standard theory because we know that compact manifolds with boundary, the operator will be Fredholm. So we automatically have a parametrics there. And then we glue the two parametrics together to get a parametrics on the whole space. So that's how we get that the operator is actually Fredholm. And then we want to do index theory. And lucky for us, someone already computed this in the case of straight cones. So our cones are not straight yet, but we can do some deformation argument and then use an index formula which goes back to Chou from 85, which yields us again a harmonic spinner on this manifold with cone-like singularities. And the other ingredient that we always need for the proof of Llarull is the Schrödinger-Llarull formula, but we only need the integrated form of it. So the integrated Schrödinger-Llarull formula. So this, you also show this still holds for manifolds with cone-like singularities. So here we do some exhaustion. So we take sections that are compactly supported, so supported away from the cone points, and then take a limit. And then it turns out that the integrated Schrödinger-Llarull formula still holds in the setting and with no additional terms or so. And then we just can repeat the estimates that also the same estimates as in Llarull. And then we can actually conclude that yeah, that's isometry. Because I mean, okay, in the case of the theorem 2, where we considered the spherical suspension, we already knew that it's a local isometry. What we needed to know is that it's orientation preserving or reversing almost everywhere. but now we again have this property here of this harmonic spinner, and we can repeat this argument from these 2 pages, and then can conclude the same thing as here, and actually have shown that the map F is a metric isometry. Okay, so that's the point where I wanted to stop. Thanks for the attention.
Yeah. Hello.
Yeah.
Yeah. So I guess me and Sandeep is only there. So Sandeep, do you have any question?
No, I don't have any.
I mean,
Okay.
I admit that now today it was a bit sketchy at most points. I hope that the general idea kind of got clear.
Yeah, at least the main theorem was like it was related to the previous talk. So
Yes. So
yeah, of
So,
course, the
kind of,
proof like probably I did not understand fully, but yeah.
yeah, I mean, I left out a lot of details.
yeah.
Yeah, of course, it's a paper, so you cannot
Yeah.
give the whole proof. So that's almost impossible. But yeah, the theorem is like nice. So I was like thinking last time, like, let me just see. Last time I was thinking something, I forgot what. Because basically last time I thought, so.
So in the 2 days, in the especially your cone-like singularity thing, so there I'm just wondering where like, yeah, in this thing, so the regularity for ape, you don't assume to be anything, it's just ellipses is only enough. Like ellipses is kind of W1 infinity kind of things, right? Or like,
yeah. I mean, in case that Wn plus 1, yeah, I mean, this L infinity would mean that the links here, so this del K, it has to be a sphere, because in L infinity you start with a closed manifold,
okay.
and then allow singular metrics, so metrics that are singular in points. So the situation here is a bit different, because as links, so as this boundaries, we also allow general manifolds. Yeah, so it's not that one definition is included in the other, or the way around. So there are intersection points, but they are not totally related.
Okay. So and the in the punctured sphere, you mean the metric is still like how do you define the on the punctured sphere the metric like the restriction of the round metric or kind of like how is it defined?
I mean, yeah, I should say so. Not every affinity metric is a cone metric.
Oh,
It can be more flexible near the singular points.
okay.
So, yeah. yeah.
Okay, okay.
So
Yes,
I was
yes.
basically asking last time when you did the theorem of, I guess there, instead of you like, can you go to the last theorem, not the today? Yeah. So there,
You mean
yes, just a
Llarull?
minute. Yeah, just 1 second. Yes. Yeah, so F was smooth, and then you, instead of smooth, you change it to something, I believe.
Two Lipschitz, yeah.
Yeah, to ellipses. Then I was asking, have you tried using like not even Lipschitz with LP regularity or something?
I mean, the thing is that we really depend on that the map is differentiable almost everywhere. This is a theorem of Rademacher, which says that every Lipschitz map is differentiable almost everywhere.
Yes.
Otherwise, we couldn't do this estimates in the Schrödinger-Lichten average formula. So you kind of would need something like that to
I
do.
see. Okay.
Maybe I can do one more remark. So people are, when doing these generalizations, ask also what assumptions do we really need. So as we saw in this theorem 2, we can relax the assumption on the metric, we can relax the regularity of the map, which is still an open question is if we can get rid of the spin assumption. I mean,
Nice.
for the proof, we definitely need spin. In dimension 4, there was very recently, I think last year, a paper that showed that the rule is also true in dimension 4 without spin.
I see.
But up from dimension 5, it's still an open question. So they use minimal hypersurfaces, and I mean this method is restricted to low dimensions. So yeah, that's still open.
I see. Okay. Okay, yeah. So I was having basically this question I was having from the last time. So yeah. So
Yeah.
thanks. Okay, then yeah, then we can probably stop for today's session.
Yeah.
Really, thanks, Lucas, for your wonderful series of lectures. It really gives
you're
a
welcome.
overview on the spin geometry as well as in the current work
Yeah.
I have presented. Yeah. Yeah, we can stop, and thank you, Lucas, again.
Yeah, you're welcome.
Maybe we'll meet again in Sergio's talk next week. Let's see.
Yeah.
Okay. Bye.
Yeah. Bye.